Welcome student to this example where we will examine the continuity of a function called Thomae function. It's from 1875. This function is defined by the type of x. If x is a rational number of the form as a fraction m over n, in its simplest form means if there's any common factor we cancel it. The GCD between m and n is 1. It's the simplest form. The function will return only the denominator and will make the numerator equal to 1. However, if x is rational, the function will just ignore it and give you 0. This is a very interesting function because of the property that this function will turn out to be discontinuous at every rational number. However, it is continuous only at the irrational numbers. So, to solve this question or to show that this fact, we have first to show that the function is discontinuous at every rational number. So the proof will go as follows. We will use the sequential criterion for continuity, which means we will assume f is continuous. So it's kind of a proof by contradiction. And we'll take a rational number q equal m over n be a rational number in its simplest form. Now, moreover, I will take a sequence, let alpha n be a sequence of irrational numbers that converges to q. We know that such a sequence always exists by the density theorem. For any number, we can find a sequence of rational and a sequence of irrational. This time, I will choose a sequence of irrationals that converge to q, which means the limit of alpha n equal to q. Now, let's see what happened if we apply f to both sides. So if you put f here and f here, this would be q and this would be limit of alpha. Of course, the function, and because the function is continuous, we can just directly exchange. So it would be this one, alpha n. F of a q, now remember q is rational, so f of a q will be just 1 over n to the side. However, alpha n is irrational. So f of irrational directly equal to 0. So what we will end up is 0 equal to 1 over n, which is clearly a contradiction. And thus we prove that the function is discontinuous at every rational number. Now, for the second type for proof, we will use the epsilon delta definition of continuity. Why? Because here I need to prove that this function is continuous at every rational number. So how we will gonna do this? So we'll assume that my number is c, which is a rational number. We will show that f is continuous at c. How do we prove that function is continuous at c? Let epsilon greater than 0 be given. And we write what is required from us. Remember epsilon delta definition, what is required from us is to find that there exists delta greater than 0 such that for any x with the fact that x minus c is less than delta, then we get f of x minus f of c shall be less than epsilon. Of course, we know information about f of c because c is rational. This means this is equal to 0 because c is rational. Okay, so far so good. We need to find delta which is greater than 0. The idea here is I will use the Archimedean property. So by the Archimedean property, there exists a natural number n capital such that 1 over n is than epsilon. Now, how do I know that I might need to invoke the Archimedean property? Remember, my function with the rational is 1 over n. So f of x somehow might be equal 1 over n, and I need to prove that 1 over n is less than epsilon. And the only way we think about this if we use the Archimedean property. Now, after we find n capital, still I didn't do anything with small n, the general n, but now I will find delta. So now choose delta to be greater than 0, such a number, such that in the interval of x, which is x minus delta, oh sorry, not this one, it's the c, the interval of c contains only rational numbers x equal m over n with n greater than n. Now, by the Archimedean property, we find n capital. Now I will take an interval that contains only the rational numbers that they have denominator greater than n, which is always I can do. Think about it. Assume that n is equal to 10. Then you can find an interval over C which only denominator greater than 10. This is something we always can do. Otherwise, the numbers x will be unbounded if we have only less than n capital. Now, that being said, we have the following situation. Now we can say that we find delta. Now I will assume this one and I will work with the left hand side. Now assume x minus c less than delta, which means x is exactly in this interval. Now, if x is rational, we know the fact that x equal m over n, and we know that n is greater than n capital. So, what is f of x minus f of c? It is equal to f of m over n minus f of c, which is 0. So it is just f of m over n, which is 1 over n. But we know that 1 over n is definitely less than 1 over n capital, and this by the Archimedean property less than epsilon. So we are done. If x is rational, now x could be irrational. So f of x minus f of c. Now both of them are rational. This means the first one is 0, the second one is 0, the final answer is 0. However, the 0 again will be less than epsilon. So in both cases, I will get epsilon. And that's how we prove the Thomae function is continuous at every rational number. Thank you for